Hello, my name is Ray, and today I would like to go over section 13.5, and more specifically theorem 13.8, which is the the chain rule with implicit differentiation. So before I go over specifically 13.8, right, I want to go over specifically chain rule with one independent variable. In this case, it would be dw over dt is equal to partial differentiation of dw, the partial derivative of w over partial derivative of x times dx dt, the total differentiation over partial derivative of w over partial y times dy over dt. Now, the reason why I want to go over this is this is the basis of our theorem in 13.8, and I want to explain this. So in this case, w would equal to f, x, and y, where x I would be like let's say gt, and then y would be something like ht, right? And then the variable w, right, is dependent on x and y, and depending on the indirection, we want to find the rate of change of w, and that's why we have dw over dt, and that's why we split it into these two partial differentiations. So specifically, what is partial differentiation of w over partial differentiation of x, right? In reality, what this is it measures the change at which w changes based on x if we hold y constant. And this is vice versa for the partial differentiation of y over partial w over partial y. And these derivatives basically indicate how x and y will change with respect to the overall overall t. And that's why we multiply with x and y. So to get a bit more deeply into why we multiply with partial differentiation of w over x with the total differentiation of dx over dt, it's because the chain rule, in this case, the chain rule aggregates the individual impacts of t and w through x and y. And these two terms itself computes basically the contribution of the rate of change of w because of the rate of change in x, which then in turn basically makes it due to the rate of change of dt. And that's where we get our entire equation of dw over dt is equal to partial w partial x multiplied by dx over dt, and same thing over here. So another way to sort of understand this would be if t is sort of the primary mover that affects w, right? And which you want to move it through both the variables x and y. And using partial differentiation, we can combine these two movers into figuring out the total rate of change of w. So now we know where theorem 13.6 comes from, right? So what our theorem 13.8 uses is actually a variation of this, which is what we call chain rule with two independent variables. And what that looks like is something like is when you have, let's say, our equation w has s and t. So let me explain this a bit better. W can equal to fx and y, and where x itself can be not in this case not gt, but it can also be g s and t, and then y would be the same, could be h s and t, right? And here we have these two variables that we do not know what to do with them, right? We can't put it into this equation. We don't really know what to do. What's interesting about multivariable calculus is that because these are two variables, we can actually turn this into a partial differentiation equation, right? So we can turn this into partial w over partial s, or since we have another variable t, partial w over partial t, right? And these are two separate different partial differentiations, and we can do this. Remember, partial differentiation is holding one variable constant while differentiating the other to figure out your derivative, right, in this direction. And because we have two variables, we can do it to both of these variables. And in this case, because of that, we have partial w over partial s, which is equal to partial w over partial x times partial x over partial s plus partial w over partial y times partial y over partial s. So if you actually look between, this is, I want to clear 13.6, theorem 13.6, this is theorem 13.7, This is theorem 13.7. If you look at the difference between 13.6 and 13.7, in reality, there isn't that much. The main difference you see is the partial differentiation here, as well as the changing the two separate variables we have up here, right? And another thing you might notice is we have partial derivatives here instead of a total differentiation over here. And a reason for this, right, is because x has two variables now, right? You can see it's in S and T, same with y, it's S and T. We have to partial differentiate it based on we have to partially differentiate it based on S because we're finding our total our bottom partial as S as well. So let's get into basically theorem 13.8, which is specifically more specifically, I want to talk about the partial the implicit differentiation between z if we have the equation of, let's say, w is equal to f x y z, right? So in this case, I want to basically prove the equation of negative, f partial x partial f over partial x over partial f over partial z is equal to sort of partial z over partial x, right? And the way we can do this is specifically, I want to mention is if f x y z is equal to 0. And so let's say we have an equation x squared plus y squared plus z squared is equal to 25. To make to allow for partial differentiation, we have to move 25 so our ending variable is 0. To be more specifically, we want to prove this equation, right? So let's set we know that x squared is an independent variable, right? This is also an independent variable, but this is a dependent variable, right? This is dependent on whatever this is set, and you can rearrange this however you want, as long as you want. X squared can be independent. This can be, one of them has to be dependent based on what happens between the other two variables. And so in this case, we can set, I don't know, x can equal s and y can equal t, right? We use theorem 13.7 to be put we use 13.7 to prove implicit differentiation in theorem 13.8. So back to what I'm saying, right? So we have our main theorem, which is negative f over x over f over partial z, right? And then we want, so to figure this out, we want to figure out these variables, right? So we want to partial differentiate f over partial s, so we can use theorem 13.7 itself in our equation. So this would be f over x times partial x over partial s plus partial f over partial y times partial y over partial s plus partial f over partial z times partial z over partial s, right? And in this case, we immediately see, right, that this partial x with respect to s, since we set x to s, this would equal to 1, right? This would be equal to 1. Here, partial y over partial s, let's look at back here. We set y to t, right? Not s. So this would be 0. So we would put this would equal to 0. This would completely cancel out. So to organize this a bit better, so we have, and partial f with respect to s would also go to 0. So because our original equation doesn't have that variable. So to organize this, we would have 0 is equal to partial f over partial x times 1 plus partial f over partial y times 0, which this would obviously cancel out to 0, plus partial f over partial z times partial z over partial x. Now, if you recognize what we're trying to find here, you can obviously recognize that we did not copy this down directly, right? We changed, these two don't seem like they're the same. But in reality, because we set x to equal to s, and because this equation we're using so-called gangster math, we can change this variable s into x. And what does that give us? That gives us the exact thing we're trying to find, which is partial z over partial x. And if you rearrange it just a bit more, you can move this here. That becomes negative partial f over partial x is equal to partial f over partial z is equal to, you're trying this, which is partial z over partial x. Move that over, and you get our final equation, which is partial f over partial x over partial f over partial z, which is then equal to our total our implicit differentiation of partial z over partial x. And that's how you know how to sort of prove your implicit differentiation, and you know where it's coming from, how it's used within chapter 13.5, as well as continuing this forwards with your other equation, your other implicit differentiations, such as you can use this exact same concept in, let's say, partial z over partial y as well. So yeah, thank you so much for listening. I hope this gives a bit more clear understanding of how things work, how things are connected throughout this chapter. And yeah,